afternoon to our GIS demonstration fair, vendor demonstration fair. What we did today was we invited vendors to come in and display their wares. We invited vendors to come in and show us what they had, and in addition to that, we invited people from on the university campus and from various agencies around the state who've been doing work with GIS to show some of the work that they've done. And so I think that went quite well. The idea for this afternoon started with a seminar course that we got together and presented this spring, for which we did a series of lectures on GIS, and currently for the second half of the semester are doing some hands-on work with some of the various systems that are available on campus. And that seminar course has been very well received. We had over 70 students sign up for it, which was more than we had bargained for, so we had to change rooms right at the beginning, but we were able to accommodate people. What this demonstrates is that GIS is growing very rapidly, and it's being used in more and more fields, and that students here at Iowa State need to have this kind of an education to remain competitive in the job market when they graduate. So in response to that, we're hopefully going to, in the fall, be having our first GIS course, and to be followed up with one in the spring as well. Those will be based on the National Center for Geographic Information Analysis core curriculum. So that will be coming up hopefully in the fall and the following spring. So that's sort of why we're here today, why we got the vendor demonstration together today. And to wind things down here this afternoon, what we did was invited Mark Armstrong from the University of Iowa, who is a associate professor in the departments of geography and computer science. Mark has degrees from State University of New York at Plattsburgh, degrees all in geography, from the University of North Carolina at Charlotte, and a PhD from the University of Illinois. Mark's research and teaching interests include spatial decision support systems, database design and management for spatial applications, and spatial analysis and computer techniques. Mark has published widely in many refereed journals, including the International Journal of Geographic Information Systems, the Journal of the Urban and Regional Information Systems Association, and Cartography and GIS, each of which are some of the most prestigious journals in the field of geographic information systems. In addition to his publishing in these journals, he's on the editorial board for Cartography and GIS and Computers and Geosciences, and he also serves as referee on both of those and several other very well-known journals. So with that introduction, let's welcome Mark Armstrong.
Well, that was quite the introduction. I'm almost embarrassed. I'll try to avoid doing my Larry Bud Melman impersonation when I start talking into the microphone and then turn my head away. For those of you who watch Late Night with David Letterman, you know what I'm talking about. When I got the flyer that described this presentation, what I do for my students is I hold this into the light so that they can see it. It said that I was to be giving the featured presentation. When I looked at that, I tried to say to myself, is that a compliment or not? Because when you talk about computer systems, oftentimes you might hear vendors say, well, that's not a bug, it's a feature. So I'm really having some dissonance about whether, in fact, I should be flattered about making a featured presentation. What I'd like to talk about today is some of the work that I've been doing for several school districts in Iowa, and I've also done a little bit of work for the Charlotte, North Carolina school district as well. I'll talk a little bit about the notion of having and developing a spatial decision support system, and we'll talk a little bit about what the specific problem that I'll be focusing on is. We'll talk about GIS-based demographic analysis and a method that we've developed to make population projections for very small areas. And by very small areas, what I'm talking about are city blocks. And those of you who've made population projections know that this is either foolhardy or we've developed a nice method to be able to do this. And finally, towards the end, I'll talk about some of the results that we've had in this work that we've been doing. I'll talk a little bit about spatial decision support systems. I'll be brief in my comments here. The general philosophy of a spatial decision support system is essentially one in which we're working with semi-structured problems. And by semi-structured problems, we are really dealing with problems that have aspects that are not readily quantifiable. That is, aspects that do not lend themselves to really incorporating themselves into a digital geographic database. Typically, we're talking about problems with competing objectives or conflicting objectives. And we have this notion that we need to have some kind of a decision maker who's going to be working in some kind of an iterative loop. This iterative loop typically involves generating alternatives, evaluating the alternatives, either using measurements that are provided by the system or using knowledge that they have embodied in themselves based on their personal experience. And typically what we're doing is using the models only as a mechanism to help decision makers deal with the complexity of their problem. We're not so foolish to think that we're ever going to capture all aspects and incorporate those into some kind of a computer model. There are a lot of political things that come into play. We're very much aware of that. When we find that people use spatial decision support systems, they, as I asserted a second ago, they go through this iterative process of refinement. Typically what they do is go through a series of stages in which they try to develop in the first place some kind of a solution strategy, and when they're going through these repetitive analysis, they then tend to essentially explore the problem in that they view how different variables that are embodied in the model are going to be traded off as they change parameters and the like. And then finally what you find are people reducing the search space and trying to converge on some kind of a decision. Now the architecture of the system that we're working with, and you can see the sort of ugly loop going around here, I guess I should have emphasized that a little better. We're looking at this as having a database which serves essentially as the switching yard. For those of you who are into movies, this sort of looks like it came from arachnophobia, I'm afraid, in the sense that it does have sort of a spider-like view to it. We have the database, we have a series of modules, software modules, that we use to transform the data. When we're dealing with urban kinds of applications, we're typically trying to find shortest paths through road networks. We're doing location allocation modeling, and this is what I'm talking about, having the models, and we have these parameters that are incorporated in these models. We go through iterative process here where we generate maps and reports, send it around to the decision maker, they evaluate what's going on, and make another pass through the system. In the way in which this works, this is showing this is sort of a very general schematic view of the way that this works. Is we have a series of decision makers. If you want to envision something, you might think of a smoke-filled room at this juncture right here. Typically, we have people that are operating the system. This is our euphemism for graduate students. So we have graduate students who are sitting there doing some kind of input and generally handling all the user interface kind of issues that quote-unquote real decision makers do not like to deal with. This is going away, this transformation. We're trying to put graduate students out of work, I guess. We are working typically in a PC-based environment, and we have the capabilities then to generate either reports or maps that show the results of different analyses, I should say. Now the focus of what we're dealing with specifically is on, you might call, districting problems. And when we're talking about districting problems, we're talking about trying to develop ways in which we can draw borders around a facility such that we do not exceed the capacity of the facility or other kinds of issues that come up. For example, in schools, you cannot exceed certain racial balance quotas that are mandated by the state. So we have to know all the characteristics that are relevant to the study area. We have to understand the distribution of demand for these services, and we have to know the distribution and characteristics of existing services. That is to say, we have to know, for instance, their capacity. So we use location allocation models typically to perform these operations. We can, in fact, we do sometimes use ad hoc methods if the models are not working to the satisfaction of the decision maker. Our general goal is to try to satisfy the decision maker as best we are able. And we have an SDSS. What we're trying to do now is represent the supply and demand in a reasonable way, and what we're typically doing is representing them using links in a GIS. So we have a GIS kind of database, and what this enables people to do is to work through their problem and do things like manipulate entities in the system, obtain data for the modeling activity, so that, again, the GIS will serve as a way of moving data around and enabling us to use it in different ways. And also it's the sort of the basis for generating the maps and reports that I showed you a minute ago. So what we're typically going to do is represent supply, that is, for example, a school as a node. We'll assume that demand typically exists at nodes. In the applications that I'll show you in a few minutes, the nodes are going to be block centroids, or we can say that they exist as areas in some instances, but we're typically always going to boil it down to some kind of nodal representation and go through an aggregation process. Anytime you go through aggregation, of course, you're going to introduce some error. We introduce the links either through some kind of a distance metric. In Iowa, of course, the Manhattan metric works very well. That is, we move either up, down, left, right, or north, south, east, west, whatever you prefer. Or we actually use the transportation network, and I'll show you in a few minutes how the Tiger files come into play in this case. So that's sort of the background about spatial decision support systems. Now, to get to the guts of the presentation then, to maybe use an unfortunate metaphor, what we're trying to do now is really focus on the demand side of the equation. That is to say, if we are trying to figure out where we should draw boundaries for particular schools, attendance zones, then we have to make estimates for very small areas, and typically a block is a suitable level of aggregation that people who are working with these problems like to work with. And the method that we've developed is based on a synthesis of what you might call administrative record-keeping technology. It's essentially the notion that a lot of school districts now have relational database systems that have the characteristics of their students, things like their home address, what grade they're in, and things of that nature. We certainly have the capability to access large-scale geographical databases. I'm talking specifically about Tiger files in this case, although there are other databases such as digital line graphs and the like that are available. And then we have GIS software that has finally become very, very flexible and powerful in its capabilities. So when we combine these three resources, then we can begin to make projections for these small areas, and when we make these projections, we're really enabling decision makers to understand what's going on in their district at this small level of aggregation, and they're able to then determine where areas of growth are occurring, and also decline for that matter. And when we start building our database, this is after Jack Dangermann's figure that appeared in an article that he did on the joint US-Australia GIS conference in 1983. So it's been around for a while, nearly 10 years. He's showing what is often called the geographic data cube, in this case in which we have locational data, non-locational data, in this case the thematic component of the GIS database, and then some kind of temporal dimension. And I'll refer back to this in a few moments to show how we're going to be building a database that looks an awful lot like this, at least in a very broad conceptual level. To give you a flavor of the kinds of activities that we're trying to support in the SDSS environment, this is one very simple schematic example. I have some real examples that I'll show you in a second, in which we have a school represented there. And what the administrators typically would like to do is know if they add these blocks into that school attendance zone, will I push it over the capacity of the school, either in total or in a particular grade? Because one of the problems that school administrators face typically is whether they need to add a new section of, say, 5th grade or whatever. So we need to know that, and typically we need to know either the racial or ethnic component of the add-in, because in some instances they're engaged in doing redistricting in order to satisfy racial balance goals. So looking at these in a little more detail then, we have the student information system that contains detailed information, and what we're specifically interested in is the address of each student and perhaps their grade and ethnicity or race. Those are the three components that we have to specifically deal with. We're also typically interested in either their name or some kind of an identifier. We have the geographical database, that is the Tiger file, and this is going to contain a detailed description of the street network. And what we also need to do is, and this is sort of the linking mechanism that we're talking about now, is have the address range on each side of a city block. So what we're going to be doing is taking the student information system, which consists of a series of records, linking them to this geographical database using a geographic information system. So this GIS is the thing that's going to establish the link and do the address matching. So looking at this in sort of a schematic view, this is the student database. Typically you're going to have a lot of information about each student, where they live, where their parents live. In some instances there's a divorce, so they have 2 parent records and so on and so forth. It gets very complicated. What we typically want to know is use an abstracted version of this in our analysis. Tiger files, as I said, this is the geographical resource that we're using. These were developed for the 1990 census. They grew out of an agreement with the USGS, and they're a very good source of digital cartographic data. The Tiger refers to topologically integrated geographic encoding and referencing, for those of you who may not be familiar with it, and it is certainly a digital cartographic database. We look at some material that the Census Bureau published. We see this is their sort of flow chart for applications of the Tiger technology, the Tiger system as they call it. And what we're doing in our application is to do address geocoding. You can also see, too small, that we have, in this case we have house number, street name, address system. So this is exactly what we're doing. That is, we want to know the address of the student, and we can then use Tiger for that particular application. In rural areas, and the 2 areas that we were working in are Davenport, Iowa and Iowa City, Iowa. We do have a fair number of rural addresses. So you might have John Jones lives at rural Route 3. That's not going to work very well if you're trying to pinpoint somebody's location precisely. And oftentimes people in rural areas also use post office boxes. That doesn't work very well either. But what we can say is that the Tiger is quite a suitable geographical database for our application, especially if we can update it. This is a very simple schematic of an urban set of streets. So we've got a street pattern here. Each one of these things is a block. The Tiger file worked by abstracting this and using the center line essentially in an abstracted graph. I'm going to be flying through this fairly quickly. The way the Tiger works is they have a series of cells, what they call 0 cells, 1 cells, and 2 cells. These correspond simply to 0, 1, and 2-dimensional objects that are represented in the digital domain. So in this case, we have a 0 cell being a point, a 1 cell being some kind of a chain or a line between these points, and then we have areas which are 2 cells. Looking at this then, moving back to a stylized urban representation, the way in which the Tiger files, and I've sort of transformed this to make a fairly simple example here. We have our nodes, so in this case we have a node 27 and node 37. These would be typically a start node, an end node, and then what we have are a segment that connects the nodes, so in this case 94 would be a segment, and then we have the blocks that are on the left and the right. You can see that each one of these segments, so for example, what I'm calling 95 right here, I think I did that correctly, starts 37, ends at 629, so we're looking at this one here. The left is 25, the right is 64, the street name is Main Street. We have a low address and high address on the right-hand side, and a low and high address on the left-hand side. Note also that because we have a node ID here, we also have the capability to go in and find some kind of coordinate information. And actually in the Tiger file, this is lat long rather than some kind of planar coordinate. Now the GIS is used to go ahead and build the link between these two resources, that is the student database and the Tiger, and it's done on a case-by-case basis, that is a record-by-record basis, in which we have a student record coming in. Essentially the GIS software is matching the street name and then the range of low and high address either on the left or the right. And what we can then say is that Jane Doe lives on a particular street segment. And so we now have the capability to take the student database and tie that to a geographical location. So we now know what block face they reside on. And in addition, if we wanted to, we could certainly interpolate between these block faces and assume that all the lot sizes were the same size. We could actually locate them with a high degree of precision. We haven't been doing that. What we want to do is locate them on a block face, and then what we end up doing is aggregating to a block by cycling around the topological links provided in the Tiger file. Now, when we start doing this, we find that there are typically a fair number of problems that we're going to encounter. Clearly, the Tiger files were developed a fair number of years ago. In some instances, they grew out, the addresses at least, grew out of the 1980 GBF DIME files, so they're quite out of date in that sense. The Tiger has been updated using commercial sources, and actually they had some census people out there trying to update them. But there's always going to be a problem with the currency of the Tiger file. Currency, or the accuracy, I guess, of the student information system, that is the data about the students, is the next point here. We have students, in some instances, they have a fairly high mobility rate. And you have students moving either around a district or coming into the district from outside. And in addition, you might have students with two addresses in their record and you don't know exactly where they live. So that's kind of interesting, quote unquote. Naming conventions, what we find is when we go out and try to use this data, and this is the same all over essentially, we have the people who are building these student information systems are often the secretaries that work in the individual schools. They enter the data into, say, a Macintosh or an IBM PC database, and they make up their own spelling convention. When you go and try to match something like 123 West Main Street with something like 123 West Main Street, you get a failure in that case. And so what we've had to do is go back and build a synonym list that tries to essentially perform the match between these two, the Tiger resource and the student information system. And then finally, I alluded to this a few minutes ago, the problem of rural addressing. This works, the Tiger file works quite well in urban areas, but as soon as you get outside, you're seeing both the new residential developments occurring on the periphery of towns, and you also have people that have long established residences who aren't using a well-defined, clearly specified address. That's changing with the advent of 911 technology. A lot of rural places are coming in and they are developing their own correct addressing systems, but I've found that one of my colleagues, for example, lived at like 12 Ridge Road or Forest Ridge Road or something like that, and he lives sort of out in the country, and it's nice. The address that he has is like 923875 North Drive or something like that. And he doesn't like to use that because it doesn't have the right cachet to kind of where he lives. So there is a little bit of reluctance to adopt that addressing strategy, but the school district is trying to be heavy-handed and make people use it. We have, in this case now, if we can assign students to particular block faces, we can then aggregate, as I said, all of the students to a particular block, and we do this by grade and also by ethnicity if required, and then we build a little data cube. So in this case, we'd have data disaggregated by block. We'd move across here either by grade and or ethnicity, and then we'd also have data for a series of years. The reason why we want to do this for a series of years is because we're going to make projections. Now if we're content to just use the raw data, we can do analyses. We can certainly make maps like this that show the distribution of different components of the student population. This is showing the minority kindergarten enrollment in Davenport in 86, 87, and certainly administrators might wish to see information like this displayed. But if you're making decisions about how to redraw school boundaries, and these are quite contentious decisions, those of you who own homes may have chosen particular school districts when you purchased your home, and you don't want to have your children attending schools that you don't think are either as good as the one they're attending or what have you. So this gets into an area of contention among homeowners. So what they would like to do is, when they make changes, have them reasonably stable over some time horizon. So what we've been doing is trying to work with a new method of making population projection that builds on that data cube that I just showed you. Now, when we want to work at the block level, the real problem here is that typically you might have 1 or 0 sixth graders living on a block. You might have 3, you might have 10. You don't know, but when you try to make projections, if you're working with very small numbers, that becomes a very difficult task indeed. What we find when we try to do that is we get very, very peculiar results when we try to apply standard methods using block level data, and I'll show you some results in a few minutes that will document that. So we have the potential here for large amounts of spatial and temporal variability at the block level of resolution. So what we've done is essentially tried to pool our data resources by bringing in students from a variety of blocks, and what we do is essentially search around each block and bring in those students, and what we're assuming is that the students that are residing on neighboring blocks are going through demographic processes that are virtually or essentially identical to what is occurring on any given block. So we're saying that those blocks around a particular block are the same in terms of their processes. Now what we're also doing is applying a temporal filter because, as I asserted a few minutes ago, from year to year you're going to get some undulations in your data, so what we're doing is averaging. In this case what we have is for this block B right here, what we've got is the number of kindergartens in 88, 89, and 90, and we also have the first graders for 89, 90, and 91. And what we're going to be doing in terms of making the projections is calculating what we call a grade progression rate. So it's essentially taking those students in one year and figuring out what portion of them march into the next year. Again, to use perhaps not a very good metaphor here, you can think of a snake swallowing a rat, where it's passing through in a bulge, a demographic bulge. So we want to know how they're moving from one grade to the next. In this case, we're showing a 3-year K-to-1 progression rate for polygon B to be 0.91. Now that'll work, that'll take out some of the problems, but what we want to do is get a larger pool and try to get more stable projections and using a more stable pool of observations. So what we're doing now is we're assigning all of the blocks contiguous to a particular block, and in some instances, if we don't get enough students just using those contiguous blocks, what we want to do is bring in students from even farther away. So it may extend beyond the proximal neighborhood. By proximal, we mean the areas in which we have students directly in the next block. We might go out another block or so in order to bring in those students. And we do this, as I asserted, because we have this problem with small numbers. One of the things that we've decided in dealing with our problem is that we typically won't go too far, because if we go too far to bring students in, what we're doing is we're going to violate the very assumption that we're working with, that is, that you have similar demographic processes working. So we have is what we call a Z-limit. So if we go beyond a certain distance and we're not bringing students in, then we say we're done. We're just going to either make our estimate using what we have, and we've tried this the other way, is to just use the district-wide rate, because in some instances we only have like one student, and we really can't do that when make a valid projection with one student. So all we can do is use the district-wide rate in that case. And we also have knowledge in some instances that we shouldn't be bringing students in, because we know that there are very different demographic processes occurring. That is, in some instances, you can think of the other side of the track metaphor, or something that there might be a stream, and you might have very different neighborhoods on either side of a stream. So in that case, you want to have some kind of a constraint that will prevent people from being added in, students from being added into the filter area. So this grade progression rate that we're working with then is essentially, this looks very similar to the temporal filter that I showed you a second ago. There's a grade progression rate for a block I for grades G and G+1, so you can think of kindergarten and first grade right here. And we have the number of students in the filter area of block I in grade G. Again, we can think of this as kindergarten at year T, say 1989. And then the number of students in the filter area of block I in grade 1, or K+1 is 1, for the next year, that is 1990. And so we're doing is calculating this proportion of students, or this portion of students that are moving through the demographic process. Now this is showing a schematic of a block. In this case we've got block 12 right here, and the filter area for that block would be those blocks that are surrounding it. So I asserted a second ago we might use the ones that are contiguous with it. We might also bring in those that are not if they're within the z-limit. Now the z-limit is something, it's an empirical constant that we're using throughout a particular analysis. I don't have a good theory for specifying exactly what the z-limit is. I'm actually working on a proposal to the National Science Foundation to do some further analyses in which we'll try to use bootstrapping to get some handle on exactly what's going on with respect to the filter area here. But that's something I'm not really going to focus on today. What we end up getting is in some areas we have high densities of population, and we're going to have fairly small filter areas. And in some instances, as you move, say, away from the center of a town, we're going to have large blocks, and we're going to have fairly large filter areas. If I were to show another block in here, we'd have the overlap. So what I'm showing is that in this case, these filter areas are mutually exclusive, but every one of these filter areas could be overlapping. So there's a lot of overlapping, and what we're doing is we're just simply averaging what's going on over space. The spatial filter, this is a fairly simple worked example, although it is, I guess, a little complicated. It's a complicated process. What I want you to see in this case is we're making an estimate of what's going on in terms of the grade progression rate for this block here on the basis of these other blocks right here. I didn't fill it in around it, so we'll assume that we have other data here. This is showing the data for this block. This is the kindergarten 88, kindergarten 89, kindergarten 90, so that column right here matches with that. And then over here we have the 758, this first grade for 89, 90, and 91. So that's there. And these columns correspond in the other polygons as well. So what we have is we're dividing through these two quantities for the kindergarten for the entire area here over the 3-year period. So we have 4, 5, and 2 here for, if I can find that, this is the first grade here, 4, 5, and 2, 7, 5, and 8 are right here. The 875 is right here, and the 5, 5, and 5. So we're getting the numerator for the first grade and then the denominator kindergarten. We add all those numbers up, and we get a value of 0.97. So the grade progression rate in this case is 0.97. We found, incidentally, empirically, that the grade progression rate for most polygons, most blocks that is very, very close to 1. So the interpretation of this gobbledygook is that we're essentially taking this rate and we're going to apply it over time. So this is sort of a verbal restatement of what I just showed you. So if we have, and I inflated these numbers just to show you in a simple example here, we have 100 first graders in the filter area of block 37 in 1987, and 90 second graders, that is first grade plus 1 grade is the second grade, and the same area in 1988, the next year. Then the grade progression rate for that block is 0.9. That is, we're saying there's a 10% decrease in the enrollment between first and second grade for that block. And then what we do is we apply that rate to the existing population that is at a particular location. Then looking at another example, if we have 10 kindergartners on a block in 1990 and the grade progression rate for the kindergartners for that block is 0.9, and the first grade enrollment that we would predict for that block in 1991 is 9 students. So we apply the grade progression rate to the base population that exists at that location. Now some of you may be saying, well, you know, prove it. How does this work? Well, I've got some results here. We're still working on these results. It's sort of a standard disclaimer, I suppose, but this happens to be the truth. We are working on trying to document how good this method is. These are some preliminary results. I have an article coming out in Socioeconomic Planning Sciences, I hope this year. It's been accepted for publication subject to revision. I have a meeting with my colleague tomorrow morning that we're going to discuss how we're going to deal with the revisions. and I think we'll be able to treat them in a fairly straightforward manner. These are the schools in Iowa City, and we're looking now at the actual enrollment. What we did is we took the actual enrollment and compared the filter method to a standard cohort component method, sort of the way that people would do it without the filter, at the block level of analysis. So we projected, this is for 1990-91 data, we projected using the filter method that this would be it, and we projected using the cohort method what the result would be. What we find is that we have a very, very good correlation, essentially, between the actual values here and the method using the filter, the projection using the filter method. There are a few observations where we're not working very well. We have some explanations for this. In this case, we have, this is Hill School, and this is Iowa City, and it's called the Iowa City Community School District. What that means is that there are some schools out in rural areas that have chosen to affiliate themselves with Iowa City for what may be obvious reasons, I think, to take advantage of what's going on there. These are rural areas, and we don't have very good address matching success rates in those areas, and as a result, we're not faring very well. Roosevelt School is one that is in town, but is on the periphery of town, and what we're finding there is that there's a lot of development going on, and we just quite simply failed in that case. So we didn't get a very good match, but neither did the cohort method. You can see, though, that that's kind of interesting in the sense that we're positive and negative with the cohort method. Getting down to the bottom line, for the entire district using the spatial filter method, we're only off by 9 students. Now, mind you, this is only going 1 year into the future, but for people who are dealing with school populations, this is a pretty darn good, and I will say this, estimate. You can see what happened with the cohort method. Because you're dealing with the block and there's all kinds of variability, this thing goes shooting off in all different kinds of directions. It's very unstable, and we're off by 1,500 students. So if you're trying to make projections at this small area level of analysis, the typical methods do not work very well, and the method that we're showing does work very well indeed for 1 year into the future. We're currently working on updating our database. What we do is we want to be able to monitor this as we go through time, and we're working with the people in the Iowa City School District to enter in current data for this year to see how things are continuing to fare. But if you're close in 1 year, you're probably going to maintain some kind of closeness, but you have to watch out for different rates, and certainly these things can tail off. I don't think that anyone is going to tell you that we should be able to make population projections at the block level that will make sense 10 years down the road. I'm not certainly willing to go that far out on the limb, but certainly over short planning horizons, this works very, very well. This is showing the same method, that is the difference, I guess, showing the difference between observed and the filter method at the block level by grade now. So what we wanted to do is see whether there was any systematic problem that might occur with respect to grade. And you can see that the mean, this is by block now, we're only off by, I don't know quite what 7/1000th of a student is. If any of you want to define what that is, I'd be happy to entertain it. But we're off by very, very small amounts. You can see that they're generally balanced around 0, which is what we'd hope. This is actually a typo. This is a standard deviation, sorry. You can see also, if you examine this column, that in some instances we are off by quite a bit. So in truth in advertising, in some blocks we're off by quite a bit. And these would be areas that are either undergoing very large in-migration or out-migration of the student population. Looking at this in graphical form, again, this is the mean, and this should be the standard deviation. What we'd like to have is a set of observations that are very close to 0. We're showing that. 7th grade, we're not doing well. The other thing that we're showing is that the standard deviation is decreasing as you move through each one of these grades. I haven't come up with a very rigorous definition of why this is occurring, although one plausible reason is that we're getting increasing stability of what I want to say is lack of migration as you move into the older age cohorts. That is, parents have a tendency to settle in and not move as the students get into the school system. The other thing that we would like to see is the way in which these errors are balancing out for the different grades. What we'd like to see in this case would be distributions that have a very strong leptokurtic distribution. That is, they should be very peaked. What we'd like to have is everybody be at 0, essentially. We can see that, and this is a block-by-block analysis, so you can see we have 700 blocks up here. We're doing very well in the sense that we were smack dead on for 700 of the blocks in the district. There are, I think, around 1,000 or so blocks. And you can see that I've highlighted here the 1, so we're off by only 1 positive or negative right here in this range. And we have a very small number of observations that are out in the tails of this thing. That's exactly what we'd like to see. That's for kindergarten. You can see that it also works quite well for other ages. I just went up to grade 6 here. The trend is fairly steady in that sense. So now with this data by block, what we'd like to be able to do is be able to move blocks between different school attendance zones. We'd like to see what the effect of that is going to be on total enrollment in a school. We'd like to be able to also know what's going on here on a grade-by-grade basis. As I started out a few minutes ago saying, we'd like to know whether we, for example, have to add a 5th grade or a 4th grade to a particular school because of some kind of local demographic, you might call an aberration, something that's out of whack. So we have an abnormal number of students in a particular grade there. We need to know what's going on in some instances with the racial balance of a school. And this technique will also enable us to assign students from grammar schools to post-primary, what we might call junior high or what have you. Oftentimes, decision makers try to move students in large groups, and you can carve your attendance zones up in a lot of different ways. Now, in terms of applications, we've created a series of cartographic products that we typically use to support decision making. I'm going to flip through these fairly fast. The first kind of map that we typically use is some kind of a reference map. This is showing for the entire state of Iowa, of course. Of course, we have Ames here, one of the urban centers in the state, as is Iowa City. And this reference map is essentially to help people figure out where they are. We use that at both the state level of analysis. We've done some work with the Iowa area education agencies using these techniques. This is showing some information about the Davenport School District so people can see where the particular schools are. So we've got that kind of information, reference data. We're typically also interested in showing demand. In this case, this is showing residence locations in a very small area of Iowa City for K-12 enrollment. This is for only a portion of the database. So we now know where students lie, both in the past. This is 9091. This is a 1992 kindergarten projection. When we have the data represented in this way instead of a dot map, decision makers can go in and do their redistricting and see the effect before they even do the redistricting of adding in components into a particular attendance area. So they see now that there are 8 kindergartners on this particular block, and they like to be able to see that. They also often, this is reverting back to a supply map at the state level, we oftentimes also want to know about what the facilities look like in terms of their capacity. In this case, we're looking at student enrollment in area education agency regions. Now, when we do our analyses, one of the things I haven't talked about is that what we'd like to do is show the patterns of assignments of students to particular areas, particular service areas. And in this case, what we're showing is the assignment of school districts to area education agencies. We call these things spider maps. Again, we're dealing with arachnophobia, I guess, in essence. But we're showing the direct link. All of these things that are focused in on this particular node are going to be served by that particular node. Looking at this in a block level, this is kind of a messy map. This is showing assignments of blocks to particular schools. So essentially what we're showing here are the attendance zones of some schools. You can see that we have open enrollment policies in Iowa City, so some students are actually transporting across the school boundaries in order to attend particular schools, but that's not always the case. That is, mostly they're attending the neighborhood schools. One of the things that we found is that these maps, these spider maps, are difficult to compare. You'll have to take my word for it. These two maps are in fact different, although you can't quite tell it very easily with the naked eye. So what we've done is developed what we call a delta map. It's maybe a fairly obvious name. In essence, what the delta map is doing is it's showing the difference between two solutions. So in this case, we have is the first solution being shown by the boundary here, that's shown here, and then we have shaded in that portion of the original solution that would be assigned to a different center in a subsequent analysis. And then finally, again, zeroing back at the school district level, what we'd like to be able to do also is do analyses that are essentially done on the fly. School district administrators like to work with PCs and say, well, what happens if I move this chunk of students from this school to this school? So what we're doing is we're using a GIS system called GIS Plus. You can see at the top it says Transcad. It's actually a very similar product. We're using Transcad. GIS Plus, this is sort of a digression, is also made by Caliper Corporation. They're sort of subsets of one another. But what we're doing here is doing this on the fly, and what this enables us to do is do our redistricting application and show what the effect of moving those blocks around is going to be. So